Good morning, good afternoon, good evening, mammals. This video is for NTI day number 8, which is Monday, March the 23rd. I'm still processing all the changes that AP has made, so we're going to skip ahead in the notes straight to kinetics because, as far as I can tell, most of electrochem is out. There's only one tiny little thing in that section of the notes that we'll need to loop back to, I believe, but like I said, still processing. Going to try and make the best use of our time possible. Also, to make things flow a little better with the screencasting app, based on how it doesn't do the animations that I built into the slides that I would show you in class, I've had to change and create some slides that represent things that would have popped up on screen. So there's going to be some extra slides in here compared to yours. I also moved a couple of them around, so I'm going to post up a PDF of this on Google Classroom if you want to look at that. You have all the information that's there. I just had to add in some extra slides, so I'll tell you when I get to a slide that's kind of extra and rearranged versus yours. So anyway, I'm going to try and keep this short. The struggle's been real with me today. I'm on my third cut with this, trying to get it down to as short as possible, but it is standing in for a lecture, so bear with me. At any rate, we're going to go on to kinetics. We've already talked about thermodynamics. It's important because it tells us if a reaction is possible. Does it have a negative or a positive delta G? And it tells us how far the reaction goes based on the equilibrium constant. Does it go all the way to products? Does it barely go anywhere? Kinetics, on the other hand, tells us how fast. So this is kind of like going back to that diamond turning into pencil lead thing. It has a negative delta G, so the reaction is thermodynamically possible. And it's a negative enough delta G that it has an appreciable, not a tiny, equilibrium constant. So it goes significantly towards products. However, none of us are worried about that because it's happening so slowly. And this is why kineticists and thermodynamicists hate each other, like Hatfields and McCoys, which, should be thought of these people shooting at each other, not whatever this stuff is in Gatlinburg where you eat with your hands at a dinner show. Anyway, most of my grad school research was in kinetics, so I'm a bit prejudiced. So what we're going to talk about today is first the factors that affect kinetics, that affect the rate, and then we're going to get into one of two kinds of ways to calculate and express that rate. So moving on. Okay. Kinetics operates by what we call collision theory, which means the atoms or molecules actually have to physically come into contact with each other. This isn't gravity that's some force at a distance, or at least their electron clouds have to come in contact with each other. And when they come in contact with each other, their collisions have to meet two conditions. They have to have sufficient energy and correct orientation. And this doesn't always happen. Right now in my room, there's some wood, and there's some oxygen, and I know that that can burn and make water, but it's not happening because when the oxygen molecules collide with the molecules in the wood, they're not colliding with enough energy to actually get to products. And I'm kind of glad about that because I've got some antique mahogany furniture that's my great grandma's, and I kind of like it not burnt. So anyway, we'll look at some factors that increase the collision, the energy of the collisions, which is going to help us get over this activation energy, which represents the minimum energy that the molecules have to come together with to break the reactant bonds, to break this so it can form products. And we're going to look at anything that increases the rate of collisions, because we're going to presume that the orientation is random, so we don't have any control over that. We just need it to happen more often so that we'll get more collisions that have the right orientation. So when these molecules bump together, they bump together where the new bond needs to form and the old bond needs to be broken, because we're breaking this bond, we're forming this one and breaking this one. And so we have to have that correct orientation. So let's look at some of the factors that affect this. Since we were talking about activation energy, one of the big ones that affects that we've already talked about is catalyst. And we've mentioned catalysts lower the activation energy, so they lower this height there. And we've also talked about that they don't affect the equilibrium constant because they lower the activation energy equally. And they have no effect on equilibrium because both the forward reaction and the reverse reaction are now going to be sped up. They just get to the equilibrium position faster. One of the main ways that they do that is destabilizing whatever this activated complex is here. Whatever has to be formed on our way to products when these molecules come together and they form some kind of transition where it isn't reactants and it isn't products yet. If they can destabilize that, it'll lower its energy, and then more collisions will be able to get over this hump to get to products. So one example here is that iodine, which has 7 electrons, an odd number, can steal one of the electrons out of this bond to form a temporary bond here. And then it leaves an odd number with carbon because it has an odd number, and takes one of these, leaves one behind. These odd number electron Lewis dot structures, very unstable, very reactive, so it destabilizes that, lowers it, and allows it to get to completion. And what you can notice here is that I have iodine as a reactant. I also have iodine as a product. So we don't usually include it in the reaction because it would cancel itself out in sort of a Hess's law sort of way. So if we show the catalyst, typically what we do is we write it underneath the reaction arrow to represent that it's participating in the reaction, but it isn't a product and it isn't a reactant because it's used and then reformed by the reaction. Acids, by donating a proton, can do a similar thing. Here, what we're looking at is breaking this double bond and forming a double bond there. So this proton can attack this oxygen, giving it a positive charge. This thing is so unhappy, it's going to bury its positive self in any negative electrons it can find. And if you think about the electronegativity of oxygen, you know that a positive oxygen is not a happy thing. So it has destabilized the oxygen. So that's lowering its energy. And then that allows this double bond to be transferred here, and one of these hydrogens kicked off, forming this hydrogen. So chemically speaking, the hydrogen here and a hydrogen here are different hydrogen atoms, because this guy, let me label him green, he's now there. And one of these guys, let me label him blue, is now over here. But atoms don't have individual identities in chemistry. So as long as we've got a hydrogen ion before and after, it's a catalyst. Okay, surface catalysts, they participate in a different way. They just provide a surface that holds molecules in the correct orientation so that the bonds can happen. So the catalytic converter in your car is a big sheet of platinum. Should you ever get desperate for money and want to do something very illegal, you're driving around with a fair chunk of platinum in your car. But what it does is it holds some oxygen molecules on it, and then when a carbon monoxide comes along and binds to the surface, it provides just the right distance for it to bond with one of these oxygen molecules, forming carbon dioxide. So what we're trading is we're trading carbon monoxide, an acute poison, kills you now, with a carbon dioxide, a greenhouse gas, kills us later. Enzymes, which you've talked about in AP Bio, are basically a kind of surface catalyst. They're doing the same thing. Their participation in the reaction is just holding substrates in the correct orientation for a reaction to occur. So they're working the same way that a surface catalyst does. They aren't a reactant and they aren't a product. All they're doing is holding the reactants in a place so that they can react more easily. So, one of the things I'm going to ask for on today's NTI is for you to fill out this chart. Because just like pressure, if the AP wants you to talk about a factor increase in the rate of reaction, they want you to talk about the, wanted to have my pointer guy. They want you to talk about if that factor affects the energy of collision, excuse me, and if that factor affects the frequency of collision. And if it affects both of them, to get full points, you almost always have to write about both. Like I said, just about kind of like pressure with gas laws. Pressure is created when the energy of a gas molecule collides with the wall of the container. So you can up the energy, or you can up how many or how quickly those molecules are banging into the surface there. Same thing here. You can up the energy of the collision, so they're more likely to get over the activation energy barrier. And you can up the frequency of collision so that they're more likely to have a correct orientation. So fill this chart out with these things if it affects one or both of them. Excuse me. So now we'll start wrapping up here and talking about measuring the rate of reaction. So I have this sample reaction. N2O5 goes to 2N2NO2 plus a half an oxygen. And we find that the rate of this reaction was 0.008 moles per liter per minute. Let's think about this unit. Units are going to be important for this. Moles per liter per minute. So this is saying the same thing as these negative ones. So this business right here is just molarity. So capital M per minute. It is how much the concentration is changing per how much the unit time is changing. And so all of our rates are going to have this unit. Change in concentration over change in time. But we can think about this using some stoich too. Because if N2O5 is disappearing, that's why it has this negative rate. If it's disappearing at 0.008, that means NO2 is going to be appearing at twice that rate. So the rate of NO2 is going to be positive 0.016 molar per minute. Because for every two of these that go away, or every one of these that goes away, two of these appear. And our rate of O2 is going to be positive 0.004 molar per minute. So our reactants are going to have negative rates because they're going away as the reaction goes forward. Our products are going to have positive rates because they're being made, and they're going to be connected using your stoichiometric ratios just from your reaction equation. However, the rate may be different over the course of the reaction. So some of the graphs that you'll see for this, they will always have something to do with the concentration on the y-axis over time. So looking at how does the concentration change over time. These are all going to be reactants because they're all disappearing. And we're going to be looking at reactions that we consider zeroth order, first order, or second order. So what we can see here, this one, zeroth order, this is this linear disappearance of the reactant. So the rate that the reaction goes does not change because this is a constant rate. The slope here is the same as the slope here. And that's really what we're dealing with rate is the change. Change in y over change in x. Change in concentration over change in time. A first order does not have a constant rate. So the rate's bigger up here than it is down here. But what is handy about this is at least the rate is changing in a constant way. That the amount that it changes from here, if this was split into thirds, the amount that it changed from this slope to this slope is going to be the same as from the amount of change from the second slope to the third slope. That was a bad tangent line. There we go, a little better. Second orders, on the other hand, have a rate of change that is changing changily. We have this slope here, and then we have a very, very different slope here compared to here. So the amount of change, it changed by a huge amount from here to here, and then by a lesser amount from the second to the third. So we've got, in summary, rates that don't change, rates that change at a constant rate, and rates that change at a changing rate. But fortunately for us, even though the rates may be changing, there is something that's constant that we can hang our hat on, and that's what is known as the rate law, which includes a rate constant. These are two separate things. So if you're asked for the rate law, that's one thing. If you're asked for the rate constant, that's another. So we'll look at what it is that they're asking for this versus this. There's two ways to determine it. Today we're going to finish up on just the first way, which is known as the differential rate law. Because if you've had any calculus here, you're probably thinking derivatives because I'm talking about slopes and how much they're changing. If you've not had calculus here, we're basically going to be comparing the slopes at the beginning to the end and looking for some equation that will allow me to understand how the slope changes from the beginning to the end. Okay, so what I've written down here are the rate laws. So these whole messes here are the rate laws. And they include this K, which is our constant. And we can see why I'm wanting to write, but it's wanting to move. There we go, constant. And we can see from these equations why we've got linear versus curved graphs. So this one, we just have a constant value. We have a constant slope. This one, we have a constant times something, times the concentration. So when the concentration is big, the slope is big. When the concentration is small, the slope is small. Here we have a constant times the concentration squared. So when the concentration is big, the slope is really, really big because it's squared. And when the concentration is small, the slope is really, really small because it's squared. Now these curves can be hard to tell apart visually, especially the first and the second order because they're both curved. And even the zeroth and the first order can be hard to tell apart if the first order is just like barely curved. If it's just barely curved. So instead, how we tell them apart is we plot the concentration values on the y-axis in terms of the derivative of the functions that produce these kinds of graphs. Now, if you're calculus, you'll be with me. If you're not calculus, don't worry. We're only going to be plotting concentration by time, natural log of concentration by time, or 1 over. So you're going to try one of these three kinds of graphs. One of them will be linear, and you'll be good. Funny, I got a COVID slide here as I'm hacking my lungs up. This has actually been making the news. So we've got Italy's COVID cases versus the U.S. COVID cases. Pandemics grow exponentially. But you've probably heard people talking about flattening the curve or bending the curve. So Italy's still increasing. But is it increasing exponentially? So if they make a log plot, we can see now, here's this linear part of it. That's this exponential increase. But it's beginning to bend down. So even though it's still increasing, the slope is decreasing. So hopefully Italy is going to begin to do something like this. Looks like we've got a longer way to go. So I really hope all this staying at home works out for us. I'm going to pause and get a drink. All right, I'm back, y'all. Let's see if we can finish this up. So I've got some data here for 3 experiments. You're smart people. You can probably guess one is first order, one is second order, and one is zeroth order. So just got a real simple reaction. A goes to B. And the data here is the concentration of time, or concentration of A by time. So one thing to note here, I made the starting concentration the same and the ending concentration the same. So it's just a matter of how it gets there that determines the order. So what I'm going to hunt for a linear reaction, or for a zeroth orders, I'm going to look for something where the data in concentration is already linear. So cut it in half, less than half, no, not linear. Really big change, smaller change, no, not linear. 0.4, 0.4, 0.4, linear. This is my guy. So I'm going to make a graph of that. And the slope of that graph is going to be my rate constant. So I graphed this concentration by time. So just plain Jane concentration by time, and I get a linear graph. The slope of that is my rate constant. So this slope is negative k. So I'm going to put that into my rate law, where the rate is the negative change in A, because A is a reactant, it's going away, and it's equal to 0.008. And that's just because the rate for zeroth order, rate equals k. So one thing to note here, just kind of talking about it here, this slope is a negative slope, it's equal to negative k. Rate and rate constants are positives. The slope was just negative because we're dealing with A going away. We could just as easily be talking about B forming, and we would have a positive slope. The other thing to take note on this, because the AP exam loves to ask you about units, The units on rate, moles per unit time, has to be moles per unit time, in this case seconds. So that means the rate constant must have units of moles per second too. Okay, now let's hunt for the first order. First order makes a linear graph when I plot natural log of concentration. So I didn't plot this one. We already know that it's 0, whatever. So now I'm going to be hunting for a linear graph out of this data. Okay, 0.5-ish, 0.5-ish maybe. Almost 1, less than 1, 0.3, no, it's this guy right here. This is my linear data, so I'm going to graph that. And so now what I graphed was I graphed natural log of A. And I've got this nice linear thing here where my slope equals negative K. So my rate law for first order is rate equals K times A. When A is big, slope is big. When A is small, slope is small. Constant change in slope for a first order reaction. The units, again, have to be moles per second. So that means this one, for first order, the units on the rate constant are just per second. 1 over second, second to the minus 1. That way, when I multiply that by A, I get my moles per second. So first order per seconds. Lastly here, this has been a long one, is I'm going to be hunting for the second order. Now, like I said, we didn't do this guy because we know it's 0. And, if you remember from 5 seconds ago, this one's first. So, again, looking for linear. So, a change of about 1.5, a change of about 1.5, a change of about 1.5. This is my linear graph, so I'm going to plot that. Interesting. Positive graph. This one will be. So in this case, the slope is just K. It's not negative K because it's a positive graph. It's the whole thing with the reciprocal. I don't want to weigh you down with it. So now my rate is equal to Ka squared. So plug in my K, A squared. Units on this one must be per molar per second because I'm going to be multiplying that by molarity squared. So that cancels out when we multiply by molarity squared. We cancel one of those, and that leaves me with my desired final unit for rate, moles per second. So the rate constant has a unit of per molar per second. So the last thing on today's NTI is you do. One of these is 0th, one is first, one is second. So I would like you to determine the order. Determine the order. Determine the value of K. And write it up as the rate. So rate equals K, rate equals K times A, rate equals K times A squared. Be looking for proper units on your K as well. So this has been a really long one. Like I said, sorry about it, but it is standing in for what would basically be an entire class's lecture. So At least I got it to half an hour. As always, take care of yourself and others, practice good hygiene, and I'll see you on the flip side.